This is Tuesday, May 18th, 2021, Physics CP. I'm going to try to talk through evidence supporting the Big Bang Theory, not the television show, but the scientific theory that the universe began at a finite moment in time and space. And before I go to any kind of PowerPoint to support that, I first just want to do a review of chemistry in sort of an in-depth way. In chemistry class, you learned that every element on the periodic table is composed of unique atoms for that element. So if I were to, hold up the periodic table, you'd start looking at it and recognizing your old friends here. Ah, yes, the elements. And no doubt you're going to volunteer to tell me that the particles that make up an atom consist of the protons, the neutrons, and the electrons. And life is pretty darn good. The protons, in terms of mass, in atomic mass units, they have a mass of 1. And the neutrons have a mass of 1. And the electrons have a mass of 0. And it's not that they actually have a mass of 0. It's just that they are so much smaller than the other two that we round it off in our record keeping and just call it 0. It's about 1/2000th of these masses. More precisely, 1/1836 or something around there. So small enough, we round it off to 0. And then there's also the electric charge that goes with these subatomic particles. Well, I'm sorry, yeah, these subatomic particles. This is the part that nearly every student remembers easily. The protons have positive charge. The neutrons are neutral. Please don't represent that with a dash. And the electrons have negative electric charge. When you look at elements on the periodic table, I'll focus on hydrogen as an example. The atomic number for any element is the number of protons. The atomic mass is the number of protons plus the number of neutrons. And as you would hope, the atomic mass of hydrogen is 1 proton. But it's a little bit annoying that it's not exactly 1. Here it says 1.008. And just as a reminder, because science is good, knowledge is great, and you guys should remember chemistry class stuff, the reason hydrogen has an atomic mass of something that is not precisely 1 is because it has different isotopes. There exists hydrogen that really is exactly 1 proton. And this is by far the most abundant isotope of hydrogen. But there does also exist an isotope of hydrogen that is 1 proton and 1 neutron. So its atomic mass number is 2. We call this first isotope, we just call that hydrogen. This second isotope has its own name because it's so important and useful, deuterium. Deuterium. Also referred to sometimes as heavy water when it's an isotope found in a water molecule, heavy water. And finally, there is an isotope of hydrogen Of course, hydrogen means that by definition it has only one proton, but it has an atomic mass of 3, meaning it has 2 protons along with its one, did I say that right? 2 neutrons along with its one proton. 2 neutrons with its one proton. And this one is called tritium. What I remember about tritium is that its half-life is about 12 years. And so that means you start with some quantity of it. After 12 years, half of it has disintegrated by radioactive processes, radioactive decay. It's changed into something else. Because this is a tiny fraction that will fade away in decades, and this is pretty infrequent, the average that you find in nature of these 3 isotopes, multiply how how much this one is in nature, add to that how much this one is in nature, add to that how much this one is in nature, divide by their masses, the sum of their masses, and that's how you end up with this average that is not exactly 1. It would not make any sense for this number to be less than 1, and it makes sense that it is greater than 1, and that's because there's a bit of this and maybe even a tiny amount of that occurring naturally that leads to this average for hydrogen. So that's a quick reminder about why these atomic mass numbers on the periodic table are not integers. Why is magnesium 24.305? Well, because it's got an isotope that has 24, and then maybe one that's got 26, and maybe one that's 28, and the average of those is 24. I don't know the specific isotopes of magnesium, but I do know these are the specific isotopes of hydrogen. And since we're on the subject of chemistry, let me remind you of another aspect of chemistry, and that is there are radioactive decay processes that can transmutate the elements. Oh man, radioactive decay. And there were actually, I think 4 different types of decay processes that you were supposed to have learned in your chemistry course. One of them was alpha particle emission. So that's where you have some parent atom, and then it splits apart into an alpha particle and a daughter atom. The alpha particle is just a fancy name for a helium nucleus. Helium, of course, always has 2 protons by definition. And an alpha particle is 2 protons plus 2 neutrons, so that its atomic mass is 4. Glancing at the periodic table, seeing how close the average atomic masses of hydrogen to being exactly 4, we can infer there are almost no isotopes of helium to speak of that have more than just 2 neutrons in them. There must be a tiny amount, but not much, of helium, naturally occurring helium that has more than 2 neutrons. So this type of decay is an example of fission. There were 3 other types. I'm kind of hazy about them. One of them was called beta particle emission, and I don't think we care. A beta particle was essentially an electron. We represent that in the way Mr. Centeno does it with zero mass and -1 electrical charge. So a parent would give off an electron essentially and transmutate into a daughter. There was also positron emission. And by the way, this beta particle comes from a neutron, if I recall. So it is a neutron that emits a beta particle and therefore transforms into a proton. That was still part of beta particle emission. I'm slopping my annotations here. Positron emission is when a proton emits a positively charged version of an electron. So it still has zero mass, has a positive charge, and so the proton transforms into a neutron in the process. Crazy. So the proton shoots off its positive electrical charge, and so what's left behind is a neutron. And finally, just for completeness, because this was in allegedly your chemistry course, there was the process called electron capture. And that was something like where a proton and an electron combine to create a neutron. Okay, so try not to get too scared about this review of chemistry. I'm not going to interrogate you mercilessly on your mastery of this stuff, but I do find it useful to review this with you as we work towards our understanding of the first piece of evidence I'm going to present that supports our theory that the universe began at a finite moment in time and space, or more bizarrely, that time and space did not exist until the universe began. Wow, how's that for a thought? Okay, so a little bit more chemistry review because you just love chemistry. You wish I was giving you a chemistry test right now, I'm sure. So these various radioactive decay processes can be lumped into two categories, or maybe they're details about two categories. So one category is the category of fission, which means massive atoms break apart. And they can break into a couple of smaller pieces. They can shut off maybe just an alpha particle, or they can become, like closer to 50-50 split. But some parent atom breaks apart into a daughter and some other piece of the original atom. And what do I mean by massive? Greater than iron. And of course, always by atomic number, not by atomic mass. Greater than iron. So what does that mean? Atomic number greater than, here's iron in the periodic table, it's number 26. Fission only works for atoms that are more massive than iron. And being close to iron is pretty, I think, challenging to have fission work. So this works really well for uranium and plutonium. They're way up here on the periodic table. Uranium is atomic number 92. Plutonium is atomic number 94. That's why these were used for the first atomic weapons. They were fission bombs, where the uranium or plutonium was unstable. You might notice that the mass number is in parentheses. It's kind of a big hint that it's so unstable that we can't measure it that precisely before it disintegrates. I don't think I can explain the details of a nuclear bomb going off, but suffice it to say that radioactive decay releases energy in the process. And it's this uranium and plutonium type of high mass elements deep inside the core of planet Earth that keeps the inside of this planet almost as hot as the surface of the sun. As these elements decay, they release energy and keep our interior molten, meaning we still have earthquakes, we still have plate tectonics, we still have volcanoes, thanks in good part to radioactive decay of massive elements. And because one of the common decay processes is to emit an alpha particle, I mean, look at that. That's just a helium atom. You go to the party store and buy your party balloons that are filled with helium. The helium in those balloons was not here when the Earth was formed. All that helium has floated to the top of our atmosphere and gone off into outer space. The helium that's in the party balloons that you buy is the result of alpha particle decay of some radioactive element deep inside the Earth. And a gas pocket might form someplace, and then we find them and we extract the helium and sell it to you off at Party City or your local grocery store. So there will come a time when there's no more helium being produced inside the Earth because all the elements will have decayed to a stable isotope. But that's not going to happen this week, right? This takes a long time to happen. The other type of significant nuclear process is called fusion. And that's where light atoms, dare I use the word fuse? Sure, fuse together, hence the name fusion. And what, pray tell, do you think I mean by light atoms? I mean less than dun 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 iron. So atomic number less than 26. Oh my goodness. We're almost at the halfway point in the period, and I'm happy that I'm reviewing this stuff with you. These two together, when you look at them, mean why that is a very strange situation. Where did the periodic table come from? Why is it that we have elements that are more massive than iron? If we believe that the universe was started, well, okay. After the break, I'll tell you about how we think the universe started. We do not think it started with all of these elements present in the beginning. In fact, we think there were almost no elements present when the first elements were formed. And in 3 minutes, we'll get back to that. Okay, I'm going to finish this presentation by switching now to the PowerPoint that pretty much follows what I'd done yesterday. So there we go. That ends this segment.